let's recap. If we apply this concept to the Earth, then we can find a couple of ways to measure, in principle, Q. One is related to space, the other is related to time. It's not working. Okay. That's why it's not working. And we can look at a sort of the experimental measure of an integral Q of the Earth, looking in time, like this one, or looking in space, thinking about wavelengths. So if you change this as not t, but x, that's a wavelength. While before it was a period. It's the double nature of a wave, space and time. Okay? Good. We measured that, and we got that for a huge band of frequencies, Q is constant. And to take it simple, let's say it's 100. With the second SLS as a specified absorption peak. So to create an absorption band, we have to imagine to couple many different microscopic behaviors that can explain an elasticity from a microscopic point of view, and from a macroscopic point of view, we create this. Recap of the last lecture. Is that fine? So, we built viscoelastic models until reaching one model that is good enough also for rheology. You can study polymers with SLS. SLS has a specific frequency, has a specific dispersion, but looking at Q of the Earth, it's constant. Let's couple a set of SLS and let's create an absorption band. Is that fine up to now? Is it a yes, or are you a quantum system? Okay, let's assume it's yes. Now we have a problem. And again, let's not get lost in algebra, but let's try to understand the logic. Now we have a system with a constant Q. It's about 100. And we ask, okay, so we have an attenuation operator. So please remember, we have been studying in wave physics what we, in this course, we call the Green's function, the medium, rays, surface waves, and stuff like that. Then we discovered that the Green's function of the medium is related to the solutions that we can find in a homogeneous problem. Okay. Then we studied the source as another component of a filter. Okay? To take it simple, source term, let's put in omega. Green's function term, convolution in time domain becomes a product in the frequency domain. Now we have another one. That's called an elasticity. Actually, it should be embedded here. Actually, we studied also, the instrument. But we can deconvolve the instrument if we know how it is built, right? Good. So we have a new operator that actually is here. We can call it the anelastic operator. Okay, where is it? It's this. It's simple, but Q is constant. By the way, here we can take an important message home, because you immediately notice that higher the frequency is, stronger will be the effect of attenuation. And it's very intuitive, because a high frequency wave will sample the medium for more cycles. And every cycle, you're removing a part of the energy. So a long period wave will sample the medium less frequently. So that's why that operator is absorbing high frequencies. And you will notice immediately when, maybe with Stefano, you're going to look at maybe some acceleration time histories. And you will see how they decay faster than displacement time histories. I hope that we will be able to see them also today in the second part of the lecture. By the way, that's the operator that we have to treat. Now, let's imagine to plug in a delta into the system. Green's function, right? Okay. But now let's take a beautiful, homogeneous, infinite, elastic, wait a second, unelastic medium. If you put a delta, what are you waiting for? The amplitude will be diminished in time and space. Okay, but we have a problem because Q is constant. If you do the algebra, and if you apply, if you insert a delta into your viscoelastic system, that's it, and you compute it, well, a delta becomes this. Oh. Okay, so the delta is going to be broadened. But we have a problem because part of a signal is arriving too fast. Because if that is a delta related to a P wave, nothing can reach a receiver before a P wave. So we have a problem. This part of a signal is not at the proper place. Actually, it's not at the proper time. So we have to relax some condition here. And the only way to put this part of a signal later at the proper time is to assume that the system is answering with dispersion. It's not the dispersion that we study in wave physics, because at that time we studied surface wave dispersion, if you remember. Different periods are sampling different parts of a structure that has different velocities, and so different velocities in frequency. We call that waveguide dispersion. Now this one is different, because now the system is homogeneous, infinite. So we have maybe just a P wave. But now it has not an infinite Q. With an infinite Q, a delta stays a delta. But with Q not infinite and constant, the delta becomes this. Not good. We are violating causality principle. We're not in a relativistic domain where we can play with some tricks with ultra tachyons, I think they are called. We have no tachyons here, okay? So to put the things at the proper place, we need to assume that C, that is the velocity of the wave, has dispersion. It's a tiny dispersion, but it's there. And that's the expression. Again, these slides are coming from your textbook, so you can relax. You can check they're coming from these details there. If you want the demonstration of this, you can take Aki and Richards, and you have 5 pages. This is called Azzini's law. And it has been found in the 60s and in the 70s by different research teams applying different methods. By the way, the message to take home is a system with an absorption band, with a constant Q, not infinite, needs dispersion. And you can call it intrinsic dispersion. It's intrinsic because it's not a waveguide dispersion, it's a dispersion coming from the fact that we need to obey to causality principle. If you give a look to that expression, you see that there is the logarithm inside, so you immediately feel that it's a tiny dispersion. It's small. Omega 0 is a reference frequency. Usually it's used at 1 Hertz. The logarithm of the frequency that is different than omega 0 is a weak function, but it's fair. So now you can proudly say that also in solid mechanics, not only in optics, you know, in optics you have immediately dispersion because the speed of light is different in different media. So vacuum, air, water, whatever, and you have dispersion and you have rainbows. Here we don't have rainbows, but we have intrinsic dispersion. And that's the message to take home. So the Earth, on average, integral value of Q is about 100, constant dispersion. Okay? Logic. Final steps. To sum up, we completed the path to make velocities complex. And why we need velocity complex? To represent something that is decaying with space and time. If you want, you can think about the generalization of this expression. Because what we have been discussing today and the previous lecture is something that is allowing for a decay. A decay that is not geometrical spread. That's a different. Okay? Not this one. Now also if you take a plane wave, harmonic plane wave, we have a way to describe decay in time, Qt if you want. And you can think about a complex frequency or a decay in space. And you can think about a complex K. I prefer this view. Complex K means complex velocity. Complex velocity means complex modulus. Hooke plus Newton make a viscoelastic domain. And to sum up, the general expression is that we can imagine to replace 1 over c. Why 1 over c? Because k is omega over c, as you know, since a long time. 1 over c, it's an old friend, and we call that slowness. We defined it during the lecture in November 2019, when we introduced horizontal apparent velocity. 1 over c was called slowness. And it's there because if you take omega out, that's t minus, of course, c over x. Okay, the elastic one has to be replaced by the viscoelastic one. How to do that? Well, a real part and an imaginary part related to 1 over 2q. Y2 is there because it's amplitude and q is related to energy. So this expression becomes this. That's the new term. Okay? X over c is time, of course. If q is infinite, okay, this will go back to the original expression. That's the summary. Any typo is my fault. No tachyons here, no quantum mechanics, okay? If errors, my fault. So that's, we spent 2 hours to introduce this. And if the Earth has a constant Q for absorption band, we need dispersion. Another end of the story is this vision here, because now you can imagine to replace the velocities that we studied in wave physics and also during this course by replacing the elastic part with the real and imaginary part. In current terminology, well, that's typical slowness, okay, that's slowness. This is called attenuation, okay? And of course, it is related to Q. For surface waves, you can do the same, and you can imagine to replace phase velocity by a real part and imaginary part. That is called phase attenuation. And the conclusion is this. Because remember that when we measure an integral Q at the surface of the Earth, actually, we're measuring a Q that is coming from different materials that are downstairs under the surface. And Q values can be very different. I leave to you an homework. I know that you will never do it. But QP, of course, is related to alpha, and QS is related to beta, or VP and VS. Okay? That's trivial. Well, you can demonstrate that on average, the ratio between QP and QS is 9/4. It's not an irrational number coming from beautiful geometric things.
QP?
That's QP. Usually QP is larger than QS. And on average, it's 9/4. Hint, the answer is on your textbook. So you have just to read a piece of text like that. Now it's a little bit more, but okay. So to sum up, you see that for, let's say, sort of the sedimentary or metamorphic rocks, the values could be low, but not that low. Remember, also the lowest one is actually high, because Q10 means weak dispersion, weak attenuation, weak damping, with the terminology that we discovered. For sort of the other rocks, like bedrocks, you see that QP is getting hundreds. And we have a beautiful number of the outer core. I replaced 0 with this yesterday because I didn't like 0. In the outer core, it's perfectly liquid, as you can imagine, so there is no VS, so it has no meaning to look for QS, and the value of QP is very high. Also, water has a very high Q. Actually, in water, you can very efficiently propagate sound, as whales know. Okay, so remember that the Q of the Earth, V100, that we measured in principle at the surface, is a sort of an integral of the layers that are beyond the surface. And they can be very, very different between sedimentary rocks, with the bedrock, with deep mantle, and outer core and stuff like that. To sum up this part, what we did was, okay, we took the beautiful elastic velocities of the wave physics course, and we tried to insert some model to make this thing, this expression here, to contain an attenuation part. Going to complex numbers. Complex numbers means amplitude and the phase, okay? And if you want, you need time. Newtonian fluids, viscoelastic models, Maxwell, Kelvin Voigt, SLS, good, but we need a set of them. Constant Q for a band, dispersion. Okay, that's the logic. What's next?
The relation is working for those that or
No, you see, in some, the ratio here is 3.
yeah.
9/4, it's not 3. Okay? Here, it's another number. It's a little bit lower. It's nearer to 9/4. What I'm trying to say is that for real rocks, QP and QS are different. QP is always larger than QS. Usually it's twice. Usually can be, for some rocks could be 3 times QS. But on average, it's 9/4. Should I say it again?
It can be more than 9/4.
No. I said on average. Average is an average. It's not the max. Forget about this, okay? I give to you this table. Let's imagine to compute a column here with the ratio between QP and QS. Which kind of numbers are you going? Well, let's exclude this, that's infinite, okay? Okay. On average, it's larger than 2. Oh, well, it's always larger than 2. Well, here you can say. What I'm trying to say is that on average, for an average rock that does not exist, QP is 9/4 QS on average. For example, on average, a rock is a Poissonian solid. Poissonian solid means that lambda is equal to mu. And that means that Vp is the square root of 3 of Vs. And we used it, if you remember. Now, this is for a Poissonian solid. That's an average. The average between me and you is an average, okay? I'm sorry for you because I'm worse than you, but okay. So I'm saying this is an average if you make some assumptions. But this is your homework because there is half of the page on the textbook that is totally devoted to this. Okay? That's your homework. Now, how to go? Because the last topic that we will discuss today, it will be just a few slides about seismic hazard, is related to this. Because Q can be used for many reasons. The most beautiful one maybe, but it's not easy, is to use it as a tool for tomography, for example. So remember that every deduction in geophysics is, okay, let's create a theory that is at the base of a direct approach so that we can simulate some data. Let's look at real data. Let's start an inversion, direct inversion. That's not easy. But with this piece of theory, you can predict the values of Q, not only the integral ones, but also for different materials. And you can look for variations of Q in depth and on the lateral scale, and you can do some tomography. So it's an important tool. Q is a proxy, remember, for viscosity. That's important. It's one of the few parameters that can be related on short times on viscosity. Otherwise, you have to wait for thousands of years. And that's one side. But then there is another side. And another side can be a little bit evident from some pictures of signals. For example, this is the same earthquake, but recorded at similar distances in 2 different regions. On the top, we are in Nevada, which is on the same side of California, and it is, seismically very active. Most of the rocks there are fractured. The other one is a recording in St. Louis, it is Missouri, I guess. And it's one of the places that I was telling you that was where an earthquake 2 centuries ago occurred. Now look at the signals. They are totally different in terms of amplitude, but especially of frequency content. You see that the lower one contains much more high frequency. You see. And in some sense also amplitude. And remember that when you move from displacement to velocity to acceleration, you're pumping in frequencies. I omega minus omega squared. So with a very naive plot, if you think in terms of an amplitude spectrum of a signal, displacement, this is 1 Hertz, displacement usually has peaks before 1 Hertz, velocity is, around 1 Hertz, acceleration is at higher frequencies. Because you're pumping, you're multiplying omega squared. And high frequencies are more affected than longer ones by attenuation. Remember, E to the inelastic operator. That's omega. So you see that high frequencies are in places where Q is lower, they are more absorbed. That's nice, and you can do tomography with this. But you can also think in terms of what we're going to go in a couple of slides, an attenuation low. Now, this plot here, that is similar to what Charles Richter did when he was trying to find magnitude. So to plot amplitudes versus distance for different earthquakes, and you're waiting for a decade, right? That's why they were called attenuation lows. Actually, it's not a low, but it's better a relationship. Now you know why amplitude should decay, for at least two reasons. Geometrical spreading, it's the most important one, but also attenuation. But please do remember that you may have bumps here for two reasons. One is known to you and could be related to the radiation pattern. Because remember that the radiation pattern is a 3D object, okay? And it's embedded in the ground. So according to the depth, let's imagine to have a torch. Let's imagine that they're embedded in the depth. If my torch is going there, amplitude here can be less than amplitude there. So that's an average, again. By the way, they have been called, now they are called GMPE, ground motion prediction equations, but these plots here are one of the key ingredients for seismic hazard computation, the standard one. Now what do we see here? Peak acceleration, that in the next slides could be called PGA, peak ground acceleration. And you give a look for east and west, low Q, high Q. Same magnitude, and look at the difference. They are so different that actually a magnitude 6 in the east is giving the same effect as a magnitude 7 in the west. For Q. Because central and eastern USA usually, on average, has a Q value that is very large when compared to the west coast.
Excuse me, like, and the for example, the size effect that present.
That's the second reason by which we have bumps here. But that's coming later. Side effect, how to include side effects in this? It's a problem. That's an open issue, but modern GMPs, they have side corrections.
But then you cannot generalize like distance from the source, right? I mean,
Definitely, that's why I'm not using them. But I belong to a different school, sort of the writing school, okay? But, okay, so I told you, there are two ways to have bumps here. Source effects, like radiation pattern, but also directivity. If you are near to the source. The big issue in GMPE is how to fill this gap here. That's a big issue. And the second way to have bumps are side effects. Now in the next slides that we are going to give a look, I will show to you the case of Mexico City. And Mexico City, the case that we will discuss, is at 400 kilometers, so you have to go in the other room. I don't know which course is given there, but you should go in the other room. And you will have a big bump there. Okay, side effects are there. But this is for Q, and that's why it can have strong implication for seismic hazard. This is a plot that I was showing to you when we discussed about intensity. It was one of the ways to measure the energy of an earthquake. And as you can see, well, this is a very debated event, but in New Madrid, we are in Missouri. Well, we are in the central Midwest here, okay? Look at the yellow patch, how broader it is than V1 here. And you have to think about this in terms of hazard. Now, based on this picture here, you should say, well, St. Louis is risky as Los Angeles. Can you say that? Well, don't go to St. Louis or Los Angeles and say something like that, otherwise you're going to say, are you crazy? Because seismic activity here is very low. So the occurrence rate is very different, and that's an issue. That's an issue that should be treated by seismic hazard studies. And that's the next chapter. So the connection between Q and seismic hazard, if you want, is this plot here. It's okay up to now?
No.
No. Tell me.
I don't understand the plots.
Oh, let me show to you a node one. Have you understood this?
I remember this.
Okay, it's the same. No, look. The only difference between the two plots here, that's the Landers, that's the New Madrid. Actually, here you see it's 1118, 1811, 1812, because actually at those times there were no seismic instruments, and so, how to say it, accuracy of the location and on the accuracy of an event was a debated issue. Maybe there were 2 earthquakes. Something occurred there in those 2 years. Still, we are not sure if there were 2 events or 1, but magnitude, according to the intensity, is similar to this one. Now, look at the patches left by isoseisms. This one, on a scale, is very narrow. It's terrible, but very narrow. It's very, how to say, small. This one is broad. Okay? Good. Now, that's the same. But instead of using, look, here you have intensity. Okay? So it's the same, but without contour lines. And here there is a relation with ground motion parameters. But it's the same picture, but with different, how to say, colors. Because that one was contoured. Okay? It's the same. Now.
So conclusion from this is that in different...
Oh, no conclusion, no conclusion. Up to now. The only conclusion that we can draw from this, and especially from this, and from this, is that that part of the United States has a higher Q.
Yeah.
Do we agree on this?
Yeah.
Full stop. Then we can argue what to learn from this picture. And we can think in terms of hazard. For an hazard map, what would you do? No answers. But we will try to understand how we can try to give an answer. So, okay, so the conclusion about now, at this point, is differences in Q have a strong impact on ground motion propagation. Okay, it's not rocket science. We know it's there. Okay. Okay? The connection is this curve here, if you want. Now, what about hazard? Okay, let me cut the story short. I know, all of you know this. Now, when you speak about hazard assessment and risk assessment, remember that they are separate because in the risk we have to convolve in a very simple fashion with vulnerability. And definitely the first one is not decided by us. We can assess it, but we cannot decide it. Vulnerability on the other side can be decided. Using building codes, with evacuation routes for tsunamis, something like that. Okay? So you may have an event, but you're trying to get lower vulnerability, so to lower the risk. Now what about, usually you express the risk on a probabilistic base, trying to understand, to design, not to design, but to assess a set of events. They could be earthquakes, they could be tornadoes, they can be landslides, they can be tsunamis. Then you try to estimate the probabilities of their occurrence, and you can imagine how messy it is with earthquakes. Then you can try to associate the cost in the case of an occurrence, and try to estimate risk. So usually in a risk assessment study, you need to take care about vulnerability, and in many cases about exposure, or if you want, cost. If you're going to work for an insurance company, it's your business. Our business is try to understand how hazard can be assessed, okay? And that's why in the other slides I was putting some of the basic definitions here, but I will go very fast here. You can read them. I found 3 interesting definitions. This is coming from Leon Reiter, who was one of the first seismologists to devote a book to hazard assessment. He was working in US for NPP agencies. So he tried to separate these 2 concepts. There are some other definitions, but please do remember that hazard. I like this one because it's more connected to physics. So a physical phenomenon, that's the hazard. You have to know that hazard in English is coming from French hazard, but is coming from Arabic name of a dice. So when you throw a dice, or if you're going to gamble somewhere, you're making some hazard assessment. In italiano è pericolosità, ma lo sapete. The Italian is different, because in English we have hazard and risk. In Italian we have pericolosità e rischio. Rischio is similar, but pericolosità is a little bit different. That seems to come from periculum, coming from perilium, coming from the risk, the hazard that the old mariner republics were deciding when they were transferring goods in the Mediterranean. The peril. By the way, hazard and risk are different. And here there is another possible definition for seismic hazard. Okay? So a physical effect could be ground shaking, could be also a landslide caused by ground shaking, could be a tsunami caused by ground shaking, as we know from Tohoku. Okay, and you see, in the risk, usually you are connected with time and probability. The first, no, that was there, just to show to you the evolution. The first hazard map, maybe, that can be called an hazard map, is coming from Mollet. Long time ago he was visiting Italy, and he was there when the Naples earthquake occurred. So he produced this map that has some hotspots. Of course, here hotspots are related to the places that he had been visiting at the time. That's why you have large dark areas here, and here because he was visiting South Africa. But it's the starting. What's next? Maybe this is the first zoning map of a history. It has been produced in the Soviet Union long time ago. And it's the first one maybe related to building codes. Because remember that in many cases, an hazard map is at the base of actions to be taken when you design something, like buildings, like dams, like bridges, like schools, like hospitals, and stuff like that, highways. Okay, and this is maybe the first one. What about the modern times? And this is, okay, we should have time. If you're going to work with hazard, you have to know that there are classically two possible approaches. Actually, one is left, because one has been winning. And I want to show to you the classical vision, and it's coming from this book here. There is one copy at ICTP library. It's an old book, okay? Well, yeah, it's old. But still, it does contain all the fundamental assumptions of different steps to be taken when you're dealing with hazard assessment. And this dualism, there is the probabilistic vision and deterministic vision. Now, the basic difference is in one step. The first is not, is common to all the hazard assessment procedure that you can imagine. Let's imagine that you have a site and you want to build, I don't know, a dam, a bridge, an NPP, or a school. Or maybe, and this is going to be called the site-specific hazard assessment. Maybe you can imagine to have a grid of sites and you're going to create a hazard map for a region or for a country. But let's consider one. The first step is to say, okay, what are the possible sources that can affect this one? Physically, you should say, okay, what are the faults? Well, we have many there, maybe one here. You have to know that in Trieste, one is supposed to be just here, but I don't believe in it. By the way, you define the sources, and you can treat them as faults, with slip, or you can treat them with models as points, or as lines. Good. Then you characterize them. With what? With magnitudes. Now we know. You could say moments. Okay. It's the same. Magnitude. And once you define the ith magnitude of a source, then immediately you have a distance. And so on. Okay? So you define sources. That's reasonable. Then the second step is different. And so I think I was putting yes. Because the deterministic approach says, okay, look, I don't care about all the sources. I want to care about the worst one. Which one is the worst? Come on, it's easy. You take the largest magnitude.
Oh,
No, it's not
it's not
easy.
because
Let's imagine this is the largest one is 7 here and 6 here. Who is worse? And let's say this is 60 kilometers and this is 30.
60 is worse.
more. At times, one magnitude
It depends.
are devastating than
It depends by the building. If you're going to build a bridge, a dam, or your tiny house, it's totally different. Because remember that if I excite this with very high frequency, maybe displacement is not that large. But if I hit it at its resonance, wow. So it depends. That's why also this choice here to suddenly be controlling earthquake. Yes, but controlling what? On the other side, the probability is saying, okay, we don't care. We consider all of them, also low magnitude. And we try to weight them according to their recurrence. That's the tricky part. Because the recurrence means, okay, maybe we can use the GR law. Do you remember? I told you. the logarithm of the number of earthquakes in one period versus magnitude. So magnitude 7, 6, da, da, da. So you're waiting maybe for 100 or for 2, magnitude 6, and 0.8. What is a 0.8 earthquake? I don't know. But okay, you take care about this. So, worst all. The second step is common to both, because what they do is to use a ground motion parameter, like peak acceleration, and traditionally it was PGA, peak ground acceleration, and they use the attenuation law. Now it's exactly the plot that I have been showing to you before. Magnitude, distance, and you got a number here. Okay? Different magnitudes, different distances, and you read the number. Now, with determinicity, you're done. Because you have one earthquake, magnitude 7, you have a distance, okay, you have a number. While here, well, probability is saying we have all of them, let's weight them, let's compute a sum. It's a terrible mess that now we will debunk, I hope. And you got an hazard curve. What do you have here? Different levels of acceleration with a probability of exceedance in 1 year. Do you want to see the result?
Yes.
Okay, very good. That's the, well, also, previous slide is coming from an old book, and this map is coming from an old project that was the first project to compute seismic hazard at a global scale. It's called G-shape. G stands for global. It's not, nowadays, it has been overcome. But some principles are still there. And I want to show to you one thing. Because actually in 20 years, still one message, and I don't like that message, is still there. Now if you read the caption, you see here, peak ground acceleration, PGA. Wait a second, because in many cases, engineers prefer to use G and not meters per square meter per square second. That means that you have, let's say, 10 here will be 1 G. But the problem is here. A 10% of probability of exceedance in 50 years. What does it mean? Do you know? Maybe you know.
475 years of return period.
Okay, you have just solved one of their homework. What does that mean?
That it
You see that it's not easy.
Yeah.
Let's debunk it. To debunk this terrible statement here, I'm providing to you a beautiful 3 pages PDF file that you have, I think I put in both ICTP and UPS Moodle sites, and it's this. Okay, you have it. It's your homework. Okay? It has been done many years ago by Ned Field, that was and is one of the maximum experts in seismic hazard assessment, and it's really beautiful. Now, let me show to you, okay, let's start with this. Because the modern seismic hazard assessment actually is no more relying just on PGA. So PGA, we know what it is. Let's take home this acronym, peak ground acceleration. And let me show to you immediately its weakness. And that's why it's no more used. Okay. Let's give a look to these 2 signals. Don't read the 2 captions. But read the time scale here. Seconds, seconds. Good. Let's read PGA. It seems the same. 0.7, 0.8 G. Which one is worst? Don't look at the caption. Which one is worst? They have the same PGA, so they should be worst in the same fashion, right?
With a different plan.
Look at the wiggles here. Here it's a long period. Now, that's a 6.7 Northridge earthquake. A lot of damage had been caused by this earthquake. This is a 4.7 in Ancona, central Italy, in 71. Pretty much nothing happened. Just to tell to you that a peak of the ground, especially in acceleration, can be a fake. Let me show to you this. No, wait a second. This. This has been recorded during the Tohoku earthquake in Tsukidate. If you read now the scale here, that's 3G. Now if you report to an engineer 3G, it's beyond most of any seismic code in the world, and it is worse than the seismic code in Japan. We will get back to this picture later. We need a translator first, not from Japanese, but from this picture. But give a look to this. That's a 3G. So you could say, oh, well, Japan has been tragically affected by this earthquake, but not in Tsukidate. Because what occurred in Tsukidate was this, this, and this. Okay? So some damage, but nothing compared to what occurred in other places with a smaller PGA. Please do remember that the maximum value of the ground motion is important, yes, but not as much as duration and frequency content. As you know, just from my silly playing with this.
Yes, resonance.
Because my amplitude of forcing can be very small if I go to the resonance. Well, it can be very large, but the displacement varies much smaller. Okay, so about the second part of this lecture, this messy lecture, for seismic hazard, PGA was the most used parameter, but it was abused. You could ask, why?
Why?
Why? Because engineers with PGA can do Newton second law, right? If you have an acceleration, you have a mass, you have a force. Okay? If you have a building, and I'm approximating it as a single degree of freedom oscillator, you have a maximum force, external force, for which to design it. Then they do something like that. They apply the maximum, and they design this to stand this. Of course, they design also for self-standing in gravity field. That's why G is used. Okay? So it was a sort of a proxy, an easy proxy to a force. But nowadays, PGA is not the most used parameter for hazard assessment. The most used parameter for seismic hazard assessment is not a single parameter, it's a set of parameters, and it is called, if you want, SK, spectral acceleration. Now, spectral does not mean Fourier response, Fourier transform acceleration. It's related, but it's not that one. Now, let's try to understand the next definition. It's coming from the first page of an Edfield PDF, but we will use just this part. Now, let's imagine to make a simplified model of a building. Could be a skyscraper, that's easy because it has one dimension in practice. So we know that if we take a skyscraper or something smaller according to the number of floors that you have there, you can imagine to synthesize it to a single degree of freedom system. like a pendulum, but reversed. It's the same, okay? I'm putting it here. Now let's imagine to fix it here, and that's, I'm not that strong, but you can imagine to make it vibrate. Now, what decides the period of vibration of this? Only the length, in principle. Okay? So, using the Galileo's law, we have just one parameter to describe a single degree of freedom system. If you want, you can think in terms of mass and springs, and you will have two. It's okay, and then. Okay? By the way, this one is called a single degree of freedom system. So you take a building, and according to the number of floors, you make a very simple model. Like that. Skyscraper, smaller, 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 smaller. What is the minimum? 0. So you can imagine to have a set of buildings, high, long periods, shorter, 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 I cannot continue, shorter, shorter, 0. Right? Now let's imagine to take this table, it's the ground, and let's imagine to accelerate it. Who is going to accelerate it? The ground motion acceleration, an earthquake. So now we are going to apply a forcing. Now the problem is practically the same as the seismometer. You remember the seismometer? We discussed it. I have a ground motion, and I'm moving, and it's going to record the motion, right? I'm forcing the equation of motion of a single degree of freedom system. I hope you do remember. Good. Now we have to make the final step. And that's why I was putting here a slide, I hope. So here you have a complete version, the picture of net field and this. Different buildings with different natural periods. According to their height or length of a pendulum, you're going to change it from long to short, and the extreme is 0. Right? Do we agree with this? Okay, let's force it with the force of what? Of the ground acceleration. They will respond differently according to the frequency content of the acceleration. As I was silly playing with this. So all of them, they will have different time histories. More wiggly these ones, longer period these ones, because they are filtering it. Now, for all of them, let's take the maximum. You see? And you plot it. That plot is the response spectrum. You can do that in acceleration, and it's called spectral acceleration. You can do that in displacement, and it is called spectral displacement. The same principle. The same input, shaking different as DOF until 0, and that's a response spectrum. Question. Looking at this one, that is reporting acceleration. Where can you read PGA? I'm giving to you 1 second, not as a forcing, but as a time interval.
At the reference point.
Pardon? Look,
For example.
here you have spectral acceleration at 10 seconds, 5 seconds, 1 second, 0.1, 0.001. If with no building, the maximum response of no building will be PGA. I was telling this to you. Long, shorter, shorter, shorter. shorter, I can't get it shorter. At the end of the stair here will be no building. The maximum of no building will be PGA. Okay. And in principle, PGD will be on infinite period on this plot here. But let's forget about that. That's why, in some way, when you plot spectral acceleration, usually the response spectrum is plotted in period, and most of the design codes are going up to 4 seconds. Here you have SA, so now I have a set of, and here nothing. All of them are forced by the same input, that is the ground motion acceleration. And we plot here, they are going to shake. We take the maximum and we plot it. Typically, it will be something like that. The largest values will be connected to the oscillators that are, whose resonance is nearer to the frequency content of this. And if I go here, at 0 seconds, this is PGA. So, message to take home. Response spectrum is a way to couple the response of a building in its simplest fashion, as DOF, to the ground motion acceleration, plotting the maximum. Here you can read PGA. So if you have SA of t, at t equals 0, you have also PGA. And the engineers can use this. Why? Because if they know that their building is as a 1 second, okay, they should design for this acceleration and not for this. Okay? Now, jumping back and forth in this terrible lecture, actually we're just a few slides far from the end, now you do understand this, I hope, because that is response acceleration. And if you give a look to these curves here, they are coming from the Tohoku event. And these curves here are the design spectra. So they are the rules that the Japanese engineers should follow to design buildings. And you should say, how they decide them? Well, they learn. Because they learned from the terrible Kobe earthquake. It was a much smaller magnitude, but it destroyed Kobe with thousands of victims. And look at the response spectra of a Kobe event. You see this peak here? That is the most hazardous because most of the buildings have a resonance between 1 and 2 seconds. So that one had energy there. And that's why they designed this. Now this signal here is very high frequency. You see how fast it is oscillating there. So most of the energy is at very high frequency, smaller periods. You see it here. High frequency means that tiny objects will move, but large buildings will not. That's why damage was related to something small. Remember that at 20 Hertz, you hear it. So when you have energy between 5 Hertz, 10 Hertz, 20 Hertz, okay, it's very high frequency. 5 oscillation at a second. So it's very high. That's not important for large buildings. So another message to take home with the response spectrum and looking at your building, you can imagine what is the most dangerous seismic input. And that's why modern maps are not simply reporting PGA, but they are reporting SA at different periods. That's an important step from PGA, classical PGA. Is that okay? Now, let me move here, because you will see another terrible example of nature and a design code. Usually, I start my talks about hazard with this. And I'm jumping back and forth, okay? What do we have here? Well, that's the design code that was valid in Mexico before September 1985. And that code was important because it was for an important country. Every country is important, but Mexico actually is very near to California. So it's very near to very seismic active zone, and the Mexican coast and also some parts of the Mexico are very active with magnitude 8 earthquakes and larger. And they used the information coming from the recordings of California. And their engineering community was at a very high level and speaking with the Californian community. So they said, okay, let's apply a building code that is severe for active areas, and that's it. Now, remember here you can read PGA, that's a value, this is in percentage of G, so it's very high. So an engineer in Mexico should design a building that should resist to this level. But that's nature. And nature caused more than 10,000 people die in Mexico City. Because this is Mexico City. It's a famous signal. Here it is not written Mexico City. It was a seismometer, accelerometer, located in the office of the Ministry of Communication. And why that occurred? Because Mexico City was built around the old part of the city, but when conquistadores took it, was that large. And actually, if you go to the Zócalo, that is here, that is the center of the modern Mexico City, that is a huge urban area, that part is this. So most of the modern Mexico City is built on an ancient lake. You see it here. It was a quite deep lake. But in 1,000 years, refilling that part was creating a place to be where you can build things, but on soft soils. So actually, the new part, you see all this zone here, is built on soft sediments. And what occurred there was that the motion coming from Michoacan, let me show it to you, the starting, the source was here, 400 kilometers from there, and the motion was like that at the source, and you have seen the signals. Because in the lecture about strong motion seismology, I was showing to you these signals here, recorded near the fault of Michoacan. And you have them here again. Now let's give a look to their PGA. What is your estimate here? A rough estimate, 0.50 maybe, G.
Yes.
Okay? You see here a huge amount of high frequency. We are near the fault. How do we know that we are near the fault? Looking at this. Here we have near field. Okay? Remember that near field, that is the static dislocation left on the ground after a shear dislocation, can be read only in displacement. Because when you take derivatives, it's going out. In velocity, you need this, that is a long period pulse, That's directivity. So near field, near source effects. Okay? And I've been showing to you the Landers, yep, the one that was appearing before, and I told you Landers earthquake is one of the first that actually had been recorded in the near source region. But the propagation of the rupture here and the Joshua Tree and Lucerne Valley recordings are very different. Please now recognize directivity. Forward, backward. You're squeezing the signal in time, larger amplitudes, you're stretching.
Small question. PGA, is it the first peak? I thought it was the maximum peak, which is...
PGA is the maximum.
Okay. Why
Peak?
you say 0.2? I thought it was 100.
No, look here. 0, 50, 100, I think this is 120, 130. I don't care about
Oh,
that
okay.
part. But it's larger, look here.
Okay.
You see?
Okay.
That could be 20 or 30.
Okay. So like 100 and you say like...
Okay, remember, it's also connected to an instrument. If you measure it with a high frequency instrument, you can read higher ones.
Okay.
But the order of magnitude is important. Let's say 0.50. Okay.
It's due to the unit. The unit is centimeter per second square. I mean, you are saying.
Here, yes.
Yeah, we are saying the meter per second square, so it's 0.5.
Yes,
Okay,
it's
I get you.
9.8, but okay. I'm approximating things. Here you see directivity and you see it here. That's velocity. Now, while you recognize here directivity from the beautiful point of view of a rupture occurring on a near fault, okay?
Yes.
Now you can think about those two events, those two signals related to hazard, because this one is taking long time. That one is showing a large pulse, but short time. According to if you have a masonry building, this can be worse than this. It depends. And by the way, what engineers now are calling fling and directivity, and they are embedded in the new codes, please do remember that we studied them as near field and near source. So you know. This slide was just to make him bridging the gap between seismology and terminology adopted by engineers that now is common. Okay? So you know these effects. We can call them source effects. Okay? Now let me go back to this. This is a signal that is one of them may be recorded in a different place. That's why I was saying 0.50. Okay? But that's the order of magnitude. Okay, let's move far from the epicenter. Let's stay here. You see how now the signal is getting smaller because spreading and anelasticity. Now it's tiny, 0.02 G. Who cares? But now let's give a look to this one. Now we are at 400 kilometers from the epicenter. Here we have thick sediments, and thick sediments will amplify part of a motion. You should ask.
Why?
You can ask why, but you should ask, okay, but at which frequency? And this is what Stefano will discuss with you in his course, but let me give to you a simple answer first. It's a rough and simple answer. If you have a low velocity layer over bedrock, like sediments over a solid rock, and you have a thickness here, and beta is the S-wave velocity of that layer, the answer is that the largest frequency to be amplified will be this. Now, you should ask me why.
Why?
You should know. Because if you go back to the wave physics course, when we studied air columns with one fixed end and one open end, you can find the same expression there.
Yes.
And maybe you can say, oh, and the other ones are 2, 3, 5.
7.
Okay, also vibration.
So, in its simplest version, the amplification, the resonance frequency of a low velocity layer over bedrock is like the one of the clarinet, with S-wave velocity instead of the velocity of sound, and thickness of the layer instead of the length of your clarinet. Actually, it's related to the impedance contrast between the free surface, and this considered a sort of a rigid boundary, and actually the maximum amplification will be related to the impedance contrast. Oops. And you should remember impedance. Let's call it bedrock. Okay, you get the point. So lowest is this velocity compared to the bedrock, larger will be the amplification, and it will occur around this frequency. And higher resonances are 3 times, 5 times, 7 times of the odd numbers. But you will explore this and much more things with Stefano. Side effects. By the way, message to take home, local amplification, because we have a thick sedimentary valley there with low velocity velocities, and it's increasing mostly periods between 1 and 2 seconds, or let's say between 1 and 3 seconds. As you can see here, look at the different wiggles here and here, resonance. Now, look at the PGA here. It's larger than here, it's local amplification, and it's occurring at different periods. Now, if you take buildings with periods of resonance, fundamental periods around this, they will be amplified like me doing this at its resonance. Very low amplitude forcing, but strong resonance. And they can break, and they will fall. And this is what occurred. So, source effects, site effects. And please, give a look to the distance here. It's 400 kilometers. Now let's remember this, because now we are going towards the end of the story. So these are the slides. Okay. Now, this response spectrum, that is the natural one, look at the amplifications between 1 and 3. They're totally over the design, because they were not waiting for that. They had been using the ground motion, let's call it with the modern name, ground motion prediction equation of California, not of the one of Mexico from Michoacan. There was not this peak in California, not at those distances. So amplification, you can see it here, in places where the sediments are thicker. Look here, here is practically nothing. This is the Ciudad Universitaria of Mexico City, is large like a city, I can tell you. And this is the Ministry of, I don't remember which one, but this is the Santa Maria Casino. Give a look to it. Let's be strong as well. And that's the result. So in many places in Mexico City, the buildings with 20, 30, 40 stores, the new ones, in principle, well built, maybe not all of them, well built, they collapsed. So, source effects and site effects. And usually they are combined. I have to go quickly, fast now. Let me show to you, because site effects, this will be discussed by Stefano in his course. If you want to remember, they are mostly connected to impedance contrast between low velocity sedimentary layers and bedrocks. They strongly depend on subsurface topography, of course. That's why I was putting here this picture. Because, of course, you have interference of a wave field in a 3D medium, and heterogeneities will focus and defocus and amplify the ground motion. So side effects cannot be solved with the simple formulas that I was giving to you, but they can work at the first order, just at the first order. But please do remember site response estimation here. And in some way, you should try to take into account the personal behavior of one site respect to the others, given the earthquakes. This is the message to take home. And the other one was that, please do remember that source and site effects, they can combine together, especially if you are in a region like this. This is the Los Angeles Basin. It's a broad area, by the way. San Francisco, I think. I don't remember. Yes. Well, it's Southern California. Basin, it's a large area with different scenarios there. This is a result made by Kim Beck-Olsen 20 years ago. We were kids at the time. But there are 9 different sources there in the same large sedimentary basin. And you see that according to the source, amplification will be large in different patches. Because, of course, it's connected to the interaction between the wave field, local heterogeneities, local amplifications, and source effects. So it's a mess. Sorry for the word, but it's a mess. You have to remember that. And that's the end of the classical slides on this side. Let's go back to this one, and it will be the end. Because how a map is made is based on some simple steps. First, definition of sources. So you have a set of n scenarios. Your homework are 2 now. 9 over 4 QPQS, and to read this. Number 3? No, 2. Inside this one there is a third one. Let's say 2 sub 1. Okay. A set of sources. So like in my messy plot there, you have n sources, n magnitudes, n distances, and n occurrence or recurrence types that you can read on the Gutenberg Richter. Good. Your homework. Your homework will be based on this. Okay. Step. The next one is, given a magnitude, how to estimate the ground motion at a site at a given distance. This is a simple example of a modern GMP. So what I was calling attenuation law, I don't think I did right here. It's now called GMP, ground motion prediction equation. Okay. A bombastic name to do what? Here you have a parameter. Here we have PGA, for example. You have a magnitude, you have a distance, and you're based on data. Different recordings. Maybe in different parts of the world. That's the messy part. Maybe in one region, and you plot. You have scatter, of course, because you have many factors, including radiation pattern, including amplification, including whatever. You know how ground motion can be variable. So we have a scatter. But usually what you do is to assume a log normal distribution. So the logarithm of a parameter is following a normal distribution, log normal. You take the median, or you can take other sigmas here, and you're done. Magnitude 7.5, magnitude 6. Because the example that net field is carrying on in this small paper is an example with 2 sources. What you can do next is this. Now you can compute the probability of having a ground motion larger than 10, given that magnitude at that distance. What you have to do is to compute a Gaussian integral. And you can compute the probability to overcome that value of the ground motion, okay? That's why it's called probabilistic. It's based on the assumption of a log normal distribution of a ground motion parameter. That's one of the reasons. And you can do that. It's not easy. You can use codes to do that. Okay, what's next? You can express that probability of having a ground motion larger than a given value, and it will be a curve like that. For a zero ground motion, it will be 1, and then lower and lower and lower. The steepness of this curve depends on the GMP. Step number 1. Now, we assume that each of the sources has a given occurrence rate. You take the GR, log of n, magnitude, you take 1, that's 7, this is 6.5, and you read here a number. That number is called R of n, in this case here. Good. Now you take your 2 scenarios, or 3 or n, and you multiply that probability by that occurrence rate. Good. Then you sum them. Good. And the last step is very tricky. Because you assume that the occurrence of earthquakes is a Poissonian, is following a Poissonian distribution. So you can compute the probability of overcoming a given value of a logarithm of the ground motion parameter in some period, and usually 50 years is used. You should ask why.
Why?
No one knows. Someone says because it's related to the issue of the permission for NPP agency, but it was renewed in US every 50 years. Someone says because, okay, on average, the life of a normal building is 50 years. You could say, no, I want my house to live for 200 years. But, okay, no one knows. That's tricky. And then you can compute the probability to overcome the value, assuming a Poissonian distribution. That's your homework. To start from this expression, because of course, it's 1, the total probability, minus the probability that is not occurring. And from this expression, you will have to demonstrate that what is called the return period, in this case, if you use 10% of probability you will see there, is that's your homework. And your homework is 10%, and you have to look for 2%. Now, let me grab my... Okay, let me continue for a couple of minutes, then we will restart on Friday concluding this. The example that net field is discussing here is made by 2 events, 7.8 and 6, 22 years, 300 years. So you have all the numbers to do it. And this is R1 and this is R2. You can sum them, and what I like of probabilistic stops here, because this one is called actually a hazard curve. It's giving to you the rate of exceedance of a level of the ground motion per year. The next and final step is to multiply this by 50, just multiply, and to choose a value of probability to be overcome. Pay attention, because here there is a typo, because this one and this one should be reversed. So for example, now you have the hazard curve, you multiply by 50, you get this one, and you decide a percentage. Do you like 10%? Good. 10% is here, you read this value, and that's the value that you put on the map. Maybe you don't like it because you are finding that you're overcoming too much this value here. Because remember, you have 10% of being overcoming 50 years. Then you can choose 2. And now 2 is used in US. And you get a larger number, of course. You can take 0 probability and you get infinite. You get infinite really because you have a log normal that has no limit. So, using 10% in 50 years is explaining to you what is the value of O. What is it? That is written here. Okay? Now you can read the hazard map. So, a classical semi-modern seismic hazard map is plotting PGA with 10% in 50 years. That means it's produced using a probabilistic procedure. Please try to do your homework reading that very nice paper by Netfield, understanding the steps for the computation. And think about some modern issues if you want. First, most of the maps now, they present SA at different periods, not only PGA. This is no more called attenuation curve, because in many cases it's not attenuating, bumps. Now please notice that the distance of Mexico City compared to Michoacan should be read out of the plot, because here it's going until 200 kilometers. Okay? Third and last, this step here. Actually, this step, in my opinion, is not necessary, because the hazard curve is here, does not make use of a Poissonian assumption. That's a violent assumption. Okay? But if you do the Poissonian assumption, then you can put here some percentages, some periods, 10%, 50 years, and that's it. And if you use 10% in 50 years, you will get something that should return in 475 years. You have to tell me why 475. You have to tell me how much is in if you choose 2%, and you have to tell me what is occurring every 475 years. You have just to read the paper. And half of the page of Steinway section about Q. Okay, sorry, I was taking longer. Curiosity, for most of you, response spectra, PGA, PSHA are news, are new things? Yes, 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 no, no, yes, good. There should be a whole course about this. Isn't it? Okay, it's a mess. Just to tell you that the basic tools that we have been building during this course, most of them are used for seismic hazard. Site effects, source effects, you will see with Stefano. Source definition, you will see with Karim. Okay? So this can be used to study the Earth and to perform seismic hazard assessment. Okay.
Thank you.
Arrivederci. So I can communicate it to Patrizia that the exam will be on 20. Am I right? Il 20. Giusto. You are the leaders. 20 is fine for you, right? Yeah, that's a yes. You know, I have to do some inverse procedure to understand your messages. And to me is yes. Oh, okay. It's yes.
Okay, thank you.
Goodbye.
Goodbye.
Also because so that you will be more free for the next lectures.
Yeah, because if
Let's-
you have more lectures, then it gets harder. So I think it's better less lecture.
I'm pretty much sure that the first lectures by Karim and Stefano will help you also to understand this course, and sooner you learn, actually, you will see, it will be just a discussion about what we discussed, okay?
Okay.
Nothing more. What I will check is logic, not the formulas, as you know,
Yes.
okay? Okay, goodbye.
Bye.
मैंने सुना बहुत महंगाई हो गई है। ले कॉमन सी बात है।